Scientists have harnessed the power of magnetism to build the world's most incredible devices and machines. From medical marvels to construction heavyweights, here are the 15 most impressive magnetic machines. Number 15. The LHC. Built in tunnels deep underground near the border between France and Switzerland, the Large Hadron Collider was originally constructed between 1998 and 2008 and was, at the time, the most ambitious science experiment ever attempted by mankind. It's the largest and most powerful particle collider ever built, and by creating beams of photons traveling at close to the speed of light, researchers are able to smash the particles into each other at such high energies that they release even smaller pieces that aren't observable in any other situations. With a mission to further understand the most basic building blocks of nature, it takes a highly complex machine to make this possible, and at the core are a series of magnets. In fact, throughout the tunnels, the LHC has 1,232 dipoles, which are magnets that are used to bend the trajectory of the particles, and 474 quadrupoles, which are the ones used to squeeze the particles into a beam. All of these magnets are superconducting, which means they operate at close to absolute zero, the equivalent of -455.8 degrees Fahrenheit, or -271 degrees Celsius, with each one being 50 feet or 15 meters long and weighing up to 35 tons. They're so large and need to be positioned with such accuracy that a recent upgrade to the LHC meant it took more than a year to replace just 22 of the magnets. A fault with just a single one of the 1,700 magnets it needs to operate could jeopardize any experiment taking place at the time and potentially cause catastrophic damage to the sensitive equipment used to monitor the particles. Number 14. The Alpha Magnetic Spectrometer. The International Space Station is essentially an orbital laboratory that governments and scientific institutes are able to use to test experiments in conditions that are virtually outside of the Earth's influence. And in May of 2011, the space shuttle Endeavour made its final ever launch to take a particularly interesting module to the station to be installed. Known as the Alpha Magnetic Spectrometer, it was originally meant to be made up of a cryogenic superconducting magnet system, but because of the difficulties of safely using one in space, the plan was changed at the last moment to a less powerful non-superconducting version. Nevertheless, the AMS, which is an externally mounted module, has still been extremely successful at its purpose to measure the presence of antimatter and cosmic rays and further help to understand the formation of the universe and potentially even discover evidence for dark matter. Within 5 years of its installation, project leaders announced that it had detected 90 billion cosmic ray events and many hundreds of thousands of positrons coming from all directions. And while it's yet to prove the existence of dark matter in the way that had been hoped, it's already made some surprising discoveries, such as a flurry of particles being released by a nearby pulsar and what appears to be the detection of anti-helium-3, which until this point had never been seen in nature. Number 13. Recycling Plant Electromagnet. Humans create a large amount of trash, with an estimated 2 billion tons of solid waste being produced worldwide each year. Unfortunately, more than a third of this is treated in a way that's not environmentally friendly, and large quantities of the rest are simply sent to a landfill. But recent attempts at increasing the amount of recycling are starting to make an impact. The difficulty with recycling, though, is sorting materials into what they're made from, because they need to be treated in different ways to be able to reuse them. Magnets are extremely helpful with this, because they only attract ferrous metals such as tin, iron, and steel. So you'll almost always see a series of magnets at a waste management plant. They can be used in various ways, such as positioning them above a conveyor belt so the metals are lifted away from everything else, or placing them beneath so they're firmly held down while all the other material rolls away. You can also simply use a large and powerful electromagnet that's attached to a crane and swing it out over a pile of debris to remove all of the useful metallic material before it's even taken into the plant for processing. Number 12. University of Illinois MRI Machine. Magnetic resonance imaging machines are incredibly useful tools in hospitals around the world that use magnetic fields to create images of what's inside your body, from the shape and size of your organs to any objects that shouldn't be there, and they provide a useful alternative to other imaging techniques such as X-rays, which focus mainly on the skeleton. The clarity given by an MRI machine depends on the overall power of the magnetic fields it's able to produce, and by far the most powerful one on the planet can be found at the University of Illinois, Chicago. Amazingly, this machine has a 45-ton magnet, which is able to generate a 9.4 Tesla magnetic field, which is more powerful than any of the magnets used in the Large Hadron Collider, and 6 times more powerful than the ones used in local hospitals. Instead of accelerating particles, though, this one is being used to study brains, and is so accurate that it can detect sodium concentration, oxygen consumption, and even how much energy each cell of the brain is using. The combination of these 3 data points can highlight any structural issues or problems with the health of the tissue, and can detect the development of any neurodegenerative disease long before any symptoms begin to develop. Number 11. Maglev train. If you ever visit Shanghai in China, the chances are you'll fly straight into Shanghai Pudong International Airport, and one of the quickest ways to get from the arrivals terminal to the center of the city is by using the world's fastest train, the Shanghai Maglev. First opening to the public in 2003, it covers an 18.6-mile or 30-kilometer stretch between the airport and the terminus with Shanghai's metro system. And it's able to complete this journey in just 7 minutes and 20 seconds by reaching speeds of up to 268 miles per hour or 431 kilometers per hour. It's the oldest maglev train still to be in operation anywhere in the world, and required a specialized track to be built that cost around $1.3 billion. The technology is based on a design by Siemens, whereby the trains have no wheels, axles, gears, rails, or overhead cables, and instead the trains hover above the surface because of the interaction between magnetic coils on the vehicles and within the track guideway. Computers monitor the levitation more than 100,000 times per second to automatically adjust the power and keep the train around 6 inches or 15 centimeters in the air. And it's this complete lack of friction that allows them to travel so fast. Still, while it's an impressive use of technology, it's far from being cost-effective. And while high-profile lines like this can benefit from publicity and help Shanghai position itself as a future-thinking city, it's unlikely any other maglev train systems will be built anywhere else within the near future. Number 10. Magnetorquer. So much of our modern lives rely on the use of satellites, whether it be for communication, broadcasting, or being able to use location services in your car. While we take most of these for granted, it's still a complicated and expensive business to send a satellite into orbit, and once they're up there, they have to be built to last because there's no real way to perform maintenance on them. The same problem applies to refueling any engines, and this is why magnets are so important to devices in orbit. Once they're in position, they usually need to keep in the correct orientation towards Earth to work properly. Thrusters can, of course, be used to do this initially, but with all the forces and events that can push a satellite off position, it's not feasible for this to be the long-term solution. Instead, they use something called a Magnetorquer, which is essentially a series of electromagnetic coils within the satellite. There's an abundant source of energy in space from the sun, so all that's needed are solar panels to ensure the magnets can always be powered. And then they're used to create a magnetic force. What is clever about this technique is the majority of the Earth's magnetic field sits beneath the height that the satellites are orbiting at, so the onboard systems simply need to calculate the amount of torque and force needed to keep the satellite in position, and then generate that by activating the coils that push against the Earth's field. Number 9. Earth Engine. There are a number of different power generation methods that are being explored right now, from new methods of nuclear energy to alternative greener energies. But perhaps one of the most interesting is the idea of an Earth engine. If possible at a large enough scale, a device like this wouldn't need any fossil fuels and would be far more efficient with no need for combustion or side products like heat, as it can, in theory, all be done with magnets. Researcher Dennis Danzig has built several of these machines, which are large arrays of magnets positioned around each other. By altering the strength of the poles of some of the magnets, the machine is able to harness an effect called asymmetrical magnetic propulsion, which allows it to continue rotating and in the process generates around 25 kilowatts of mechanical energy, which can be turned into electrical energy. Some of the energy production needs to be put back into the machine to continue altering the strength of the magnets so it continues to turn. And even though the concept is still in its infancy, researchers in the field are hopeful it may one day be feasible. This is so far the closest anyone has been to building a true perpetual motion machine, and there very well could be a future where all you need to power your house is 1 or 2 of these in the basement. Number 8. The Maglab Hybrid. The National High Magnetic Field Laboratory, often known as Maglab, is a facility at Florida State University that's the only one of its kind in the United States and performs research into magnetic fields for a range of different scientific disciplines. At the core of this facility, and the device that gives it the edge over all of its competitors around the world, is the strongest magnet ever built for nuclear magnetic resonance spectroscopy experiments, and it's a hugely impressive machine. At 2 stories tall and costing $14.4 million to build, the 35-ton superconducting magnet is kept at a constant temperature of -456 degrees Fahrenheit, or -271 degrees Celsius, by a continuous flow of liquid helium, and 4,000 gallons or 15,000 liters of cold water per minute. Part of the reason it's so complex just to maintain the temperature is that the magnet needs 30 megawatts of power to operate, and this in itself generates a huge amount of heat. If the magnet were ever be allowed to warm up to room temperature, it would take 6 weeks to get it back to its optimal operating conditions. Within the coils of the magnets are 4 miles, or about 6.4 kilometers worth of copper wires, around the same that's used in the construction of 80 homes. And in combination, the 2 parts of the magnet, one which is the superconducting magnet and the other which is a resistance magnet, are able to create a force measuring 45 Tesla, which is 30 times more powerful than the magnetic field in the MRI machine at your local hospital. Number 7. Wind turbines. With efforts across the globe to reduce our reliance on fossil fuel-based energy and instead transition to greener alternatives, wind turbines have become an increasingly familiar sight. There are believed to be more than 57,000 of them across the United States alone, and this number will only get higher in the coming years. The gigantic structures use the wind to drive the blades, but within the main unit of each one is a series of magnets, and these are how they turn the wind's energy into power. Known as a permanent magnet generator, the magnet at the center, which is made up of an alternating north and south pole, is spun around within an induction coil. It's a basic principle of physics that in an environment like this, a changing magnetic field will produce electricity, which is the reverse process of how applying a charge to a coil will produce a magnetic field. Because the turbines use permanent magnets rather than electrically produced temporary ones, they need very little input to allow them to operate effectively. And once they've been built, they only require occasional maintenance to ensure the parts aren't wearing away, something that's particularly useful given the fact that most turbines are in tricky places to reach. Number 6. Induction Furnace. Traditionally, furnaces used in industries such as metalworking or jewelry production would have been kept at temperature by burning huge amounts of fuel. But in the same way that an induction cooking surface works at home, it's now possible instead to use electricity and magnetism to generate temperatures capable of melting metal instead. Essentially, these machines use a series of solenoid electromagnetic coils that produce rapidly reversing magnetic fields. When these are applied towards metal within the melting chamber, they cause eddy currents and circular electrical currents within the metal by electromagnetic induction, and this excites the molecules, causing the metal to heat up and eventually melt. It's a more expensive way to achieve the result than using external fuel, but there are a number of benefits that come from this approach, particularly for companies involved in producing alloys. The main one is that the heat is magnetically induced. There's no danger of any chemical contamination mixing with the melted product, which is something that would affect its overall purity. Number 5. Magnetic Head Pulley. Various industrial processes can benefit from the use of magnetism thanks to its ability to attract ferrous metals. You'll find magnetic devices within food production plants, for example, to make sure that pieces of metal haven't accidentally made their way into processed meals that are destined to be eaten. But the cleverest designs are often found in recycling plants. With so many different types of metal and material passing through these facilities, a number of methods need to be employed to separate objects, even if they've already been sorted. Recycling points around the world ask users to put cans in one place, for example, but even these are made for a range of different materials. When they're taken to the management plant, a device like a magnetized head pulley will be used to split them even further. This one, for example, holds the steel cans on the head, so everything else continues down into the collector, and then behind the main ramp, the cans that have been held are to be flattened and then removed into a different catchment area. Number 4. Magnetic Elevator. Without elevators, it would have been impossible to build the high-rise buildings that are now commonplace around the world. But while we're more than used to the designs that use a system of ropes, cables, and pulleys to transport us up and down, a German manufacturer has developed a completely new concept. ThyssenKrupp has recently revealed a test building where all of the elevators are instead magnetically powered, and this means that they're not only faster when they're moving up and down, but they can also travel sideways too. By using a similar technology to maglev trains, the elevator shafts have a series of electromagnetic circuits that will either hold the elevator cabin in place or move it on to the next section. With computer systems controlling the entire process, each cabin could potentially have its own custom route designed depending on where the passenger wants to go. And each shaft could have multiple cabins using it at the same time, as opposed to being limited to one, as is currently the case. The successful development of this technology could lead to buildings being designed completely differently, and the days waiting for an elevator to travel down all the floors to the one you're waiting at might be over. But there's clearly a safety aspect they need to overcome, and the question of whether people will feel comfortable using them. Number 3. The Calutron. The Second World War was one of the most devastating events in human history, and researchers on either side spent vast resources on the development of new, deadlier weapons. In the end, it was the Manhattan Project that ended things with the creation of a nuclear weapon, the most powerful man-made release of energy ever devised. But to do this, the scientists needed to also build specialized magnetic machines. Known as the Calutrons, they were a type of mass spectrometer, and a material would be put into one and sped up by magnetic fields, in a similar process as what happens in a particle accelerator. These particles are then deflected by magnetic fields and collide with one another, which cause the release of ions that smash into a plate where they produce a measurable electric current. What was clever about this design was that the scientists could determine the size and weight of the ions of different isotopes, with the heavier ones being deflected less by the magnetism, and by putting in the right material and capturing the isotopes they wanted, they were able to isolate high-purity uranium-235, which is the main component of a nuclear bomb. Without the Calutron, there would have been no way to produce enough of the material for a viable weapon, and the outcome of the war could well have been very different, making it one of the most impactful magnetic machines ever created. Soon after the war, though, new methods were devised for the enrichment of uranium, and the only Calutrons that remain are those that have been kept for historical purposes. Number 2. Railgun. Weapons tend to fall into two different categories: those that cause damage because they contain an explosive force, such as a bomb, and those that are destructive because they rely on the high speed of a solid projectile, such as a gun. There have long been attempts to create something that is essentially like a gun, but on a much bigger scale, and the result is something called a railgun. While the technology is still in its infancy and no one is entirely sure whether it will ever become feasible in a war setting, the United States Navy has actually managed to successfully build one. Instead of using explosive power to launch the projectile, it instead uses electromagnets, and this approach means they could be hugely powerful. They're made with two parallel magnetic rails with an armature that can slide up and down. When the current is applied to the rails, the armature is propelled to high speeds, and when it reaches the end, any projectile that's been put into it is then launched out. It's believed that launching projectiles in this way will be far faster than chemical explosions are ever capable of. But for now, there are concerns around how accurate a launch can be, and also the durability of the gun itself because of the extreme loads the components are subjected to. Number 1. Central Solenoid. The most ambitious science project ever attempted is currently being assembled in France, known as ITER. It's the creation of a new nuclear energy facility that, instead of using nuclear fission to produce energy, as is the case with all other nuclear power plants, it's attempting to recreate the processes at the center of the sun to harness nuclear fusion. This, in theory, could be the cleanest and greatest source of power ever, and if everything goes to plan, could solve our impending energy needs by the end of this century. One of the main challenges with the process, though, is that the temperatures created in the experiment at more than 270 million degrees Fahrenheit, or about 150 million Celsius, will be hot enough to melt every known material on Earth. So instead, magnetic fields will be used to contain the reaction in a ring away from the metal surfaces. A completely new type of magnet had to be designed to make this possible, and the facility is now installing the device, which is called the Central Solenoid, which is the most powerful magnet ever constructed. It's so big that it had to be built in several parts, but once they're combined, it will be 60 feet or 18 meters tall, 14 feet or 4.3 meters wide, and will weigh more than 1,100 tons. Incredibly, the magnetic forces it will be able to generate will be the equivalent to 280,000 times that of the Earth's magnetic field. It means the structure it sits within will have to be able to withstand forces equal to twice the power of a shuttle launch. The magnet itself, if used elsewhere, would, for example, be able to lift an aircraft carrier into the air, and it's taken more than 2 years to build this thing. Amazing. Watch our Machines playlist for more top 15 videos about awesome machines. Sit back, relax, and binge watch all of our best machine videos.